I will use a very simple system. Carbon dioxide, 2 oxygen molecules, carbon molecule in the middle, aligned on a line, that's called collinear, and we'll only consider the classical version of that system in which these 3 bodies are connected by 2 springs, by 2 harmonic potentials. And we will find the vibrational eigenmodes of that system to illustrate the power of thinking in terms of eigenvalues and eigenmodes and eigenfunction and eigenvectors, 1. But number 2, I will use this to sneak in a very important concept that shapes almost all of modern theoretical physics, and that's the concept of symmetry. My message will be very simple, and it'll be repeated 10 times this semester. If you have a symmetry, use it. Consider a situation in which our physical problem is defined by a Hamiltonian function. What is a Hamiltonian function? That's an operation that you apply on the state of the system and returns a number which is called energy of the system. So that's the meaning of Hamiltonian function. It's an amazing thing because it takes many dimensions, returns one number energy. But if you vary this function, you get equations of motions, which are a high dimensional set of things. And assume that there is another matrix, a very simple one. For example, you permute several directions in the space, which you used to call x, you call y, or you reverse the direction in which you move. So that's a simple matrix. The system has a symmetry. That means that the energy of the system measured once I've changed these coordinates around is still the same energy. That means that I can first measure the energy, then permute coordinates, or I can first permute the coordinates, measure the energies, and I get the same result. That's an example of a symmetry. During this course, I'll define it in 2 or 3 more ways, but that's one way to understand symmetry. If you have 2 operations with the system, the symmetry operation and the measurement observable operation, and if they commute, we say this system has a symmetry. Next, we use spectral decomposition. Anytime we have a matrix, it has its own Hamilton-Cayley equation, which I write in a form of. And the main thing about spectral decomposition is that we can use the projection operators to replace the evaluation of the matrix on a high dimensional space by the sum of ordinary scalar numbers or the eigenvalues. And if you take any matrix function, we can evaluate it as a set of ordinary one-dimensional functions returning one-dimensional number, 1 per each subspace. And we can use that to decompose the Hamiltonian into sum of Hamiltonians acting on the subspaces defined by these projection operators. And you can visualize this by saying the original Hamiltonian was a big matrix, this guy here. But now we write it as a sum of blocks where it's a small matrix in a first block corresponding to the first eigenvalue of this other matrix M. Second block, the eigenvalues of the simple matrix, let's say symmetry matrix M, block diagonalize the big thing. So instead of having calculations with d-square elements, we have a smaller calculation in each block. Now I said it in words, but let us define explicitly what is a collinear carbon dioxide molecule in the classical description. there's a carbon with mass little m. There are two oxygens with masses capital M. They're connected by harmonic or string potentials with stiffness K. At first instant in time, one oxygen is at position x1, the other one is at position x2, the third one is at position x3. So this defines the energy of the system because it tells it what the masses are and how stretched the two springs are. And now Newton's second law says that acceleration of particle 1, 2, 3 is proportional to the force it experiences, which is the stiffness of the spring, the mass of this particle, and the stretching of the spring corresponding to particle 2. The guy in the middle has its little mass k, and it interacts with the particle on the left by stretching, and the particle on the right by stretching, and the right particle oxygen interacts with carbon by stretching. So that's our system. We can write this in matrix form because it's a linear equation on the forces. We will look at a very special set of solutions for which the time dependence factors out. So let's look at solutions which are called normal modes of the system. We'll be looking for a frequency omega such that we can separate position x at time t into a variable x1, 2, 3, and the time dependence is in this oscillatory function. If we put this in acceleration, we will have to take two derivatives, bringing it down twice. And we get an equation which is just equation for the x's, time-independent equation in which the matrix of interactions, which these stiffness renormalized by the mass, so the natural frequencies, if you wish, for harmonic oscillators. What's acting on the first guy, what's acting on the second guy, the carbon in the middle, what's acting on the third guy. That should be proportional to omega squared to itself. And the secular determinant of this equation, h minus omega squared, its zero will give me the eigen frequencies of such a system. Now, this is 3 by 3 equation. So when I compute this determinant, I will get a cubic equation. You could stick this into Mathematical or some other algebraic program, but not in this course. Here, we have to think first before we compute. What I want you to do, not in the rest of this course, but in the rest of your life as a scientist, and I don't care whether you will be doing graphene or general relativity or neuroscience or big data. Whenever you approach a problem, the first thing you always ask yourself, does this problem have a symmetry? Second, if it does, you must use it. If you're not using the symmetry, you're doing it wrong. In this particular problem, an oxygen is here and oxygen is there. They have the same mass and they have the same strength of coupling to the center. So I can decide that this one is called 1 or this one is called 3. Or in this particular case, I can just flip the axis to minus x. So they are now relabeled, but obviously the energy of the system at any instant in time doesn't change because nothing depends on how I label it. So there is a symmetry, and I can write it as a permutation matrix or a 3 by 3 matrix, where I send 1 to 3, I don't touch the center, so 2 is remaining, and I send 3 to be 1. What happens to the energy when I flip it? Remember the original Hamiltonian? It had A minus A0, etc. After you flip it, A goes from here, nothing changes to the center, and the other A goes from there, and that's, you can do this calculation twice. First by multiplying them in one order and the other one, and you find the result is the same. In other words, Hamiltonian computes, it's a symmetry. Sigma is a symmetry of Hamiltonian. Observation number 1. Observation number 2, if I flip the axis and flip it again, I should be back. And indeed, if I square the sigma, I just get identity matrix. Now, sigma square minus 1, I can write it as sigma minus 1 times sigma plus 1 equals 0. So I can just write out Hamilton-Cayley equation for the system just by thinking. And I can read off the eigenvalues. One eigenvalue is plus 1, the other one is minus 1. Whenever I have eigenvalues, I'm supposed to construct projection operators. Remember projection operators? If I have ith eigenvalue, projection operator corresponding to it is a product of m minus other eigenvalues for all the rest. Product goes over the remaining ones, and divided by lambda I minus j, just so it's normalized correctly. We worked out one case where I only have 2 eigenvalues already. What happens is when you have 2 eigenvalues, product is very simple. There's only one term left, so there is no product. And there are 2 projection operators. So let's evaluate them. The first projection operator, which I'll call P plus, is to take the matrix. Matrix right now is the sigma, right here. Difference of the 2 guys is 2, so that's this 1/2. This is minus 1, so it's plus. I'll stick it in here. And this is sigma, and that's the projection operator, which I'll call plus because there's a plus here. And there's the other one where I evaluate for negative eigenvalue. Then this becomes minus 2. This guy has plus 1 in it, so the minuses cancel. And this sigma picks up a minus, so there are 2 projection operators. If I square either one of them, I'll get it back. Simple calculation. If I take a product of the 2, but that's Hamilton-Cayley, that's 0. And if I add them up, sigmas cancel, and I get 2 1/2 identities, so I have a completeness. So I have 2 spaces, and we can compute their dimensions. That the traces numbers of ones on the diagonal of the projection operator. And for this one, if I take a trace of identity, I get 3. If I take a trace of sigma, I just pick up 1. So this is 4 divided by 2. So this space is 2-dimensional. The other combination, this 1 cancels in the center. And I have 3 minus sigma, which is 1. In other words, I get 2 divided by 2, and I have dimensional space. And I've decomposed 3-dimensional space into 2 dimensions plus 1. So what? Well, antisymmetric substrate is 1-dimensional, so the matrix H is 1-dimensional, so we should be able to do that. I'll take a trace of 1-dimensional matrix just because it's easier for me to do it this way. So I'm only dealing with numbers, but trace of 1-dimensional matrix is the only entry in the matrix, so it's no big deal. So one eigenvalue is, I take Hamiltonian, multiply it by the anti-symmetrization operator, take a trace, that gives me eigenvalue. I substitute this guy, it's 1/2 identity minus the flip. What's a trace of Hamiltonian operator? It's sum of these elements. So that's 1/2 2 capital A's plus 2A. That's this term here. What's a trace of H times sigma? We had computed that one as well. The trace is just 2A divided by 2. So that gives us the second term. And we find out that the first eigenvalue simply depends on the oxygen mass. We know that that eigenvalue has to be interpreted as frequency square. So frequency square of the first mode is just this eigenvalue. What's the eigenvector? Well, just the projection operator. It's 1 minus sigma. This is identity, this is sigma. The difference is this matrix here. Eigenvector, which involves the oxygens, nothing to do with center of the mass. So this is an eigenmode of this physical system in which carbon in the middle doesn't move and the two oxygens are moving in and out in harmony. So the system breathes like that, and that's one eigenmode. What happens in a symmetric subspace? Remember, that's a two-dimensional system. And we know one thing about the system. Hamiltonian will be 2 by 2 matrix, and its diagonal will be the sum of its eigenvalues. One of them I'll call L plus for symmetric, and the other one I'll call L0. And that's, again, easy calculation. It's a trace of matrix, which we already figured out. This is that, plus the trace of reflection times H, which is just the element H. So this one depends on masses of both particles. So that means it's an eigenmode in which carbon and oxygen will move. Now it's 2 by 2 matrix. I could actually just solve quadratic equation. But remember, if you have a symmetry, use it. And there is one symmetry that's so obvious that we didn't even think about it. What happens to this system is if I translate and put it someplace else, its energy doesn't change. It's Galilean invariance of this problem. So I have a continuous translation symmetry. Whenever you have continuous symmetries, it suffices to understand what happens for infinitesimal change. So if I just change all coordinates by a little amount, then I'll find out that H acting on all coordinates should be H acting on slightly shifted coordinates, because remember what this Hamiltonian is. It depended on the distances between the pairwise distances between particles. It didn't depend on if I change them all by the same amount. Measured in any translated coordinate, these two parts are the same, H depend. And that means that the extra term satisfies the equation that H acting on the extra term is 0. And this is a matrix, so this is a matrix of 0, which I write as 1 times matrix. In other words, a 0 mode in the lingua of the subject. And the general principle is whenever you have continuous symmetry, there should be 0 eigenmodes. What is now the meaning of the other eigenmode? So now we know the eigenvalue is just a sum because this one is 0. So what's its meaning? Whenever you have a 0 eigenmode, the other eigenvector is not obvious because you can add this eigenmode to it. We can compute delta x for the eigenmode, and it just kind of changes its orientation. But in this case, there is a natural orientation. We can go into the center of mass, in which we make sure that the 3 momenta of these 3 particles add up to 0 and remain added up to 0. And the physical meaning of this eigenmode is that the 2 oxygens are going in one direction, the carbon in the middle is going in the other direction in such a way that any instant in time, the center of mass is not moving. So now, having used symmetry and totally solved this problem of carbon dioxide, we now understand also the physics of its eigenmodes. The antisymmetric solution is the one in which carbon just sits and the two oxygens go in and out in unison. The other mode is the continuous symmetry mode, saying that I can keep the thing here or I can put it there. Energy doesn't change as long as distance is the same. The energy of system doesn't change, just depends on internal distances. That's a zero mode, consequence of continuous symmetry of the problem. And the remainder is a non-trivial mode in which the carbon moves in this direction, the two oxygens move in the opposite direction in such a way that every instant in time the center of mass of the system hasn't moved. It was solved all by hand and using symmetry. When you have a real problem in chemistry or in celestial mechanics, you might have 1,000 dimensions in your calculation. You still might have a symmetry just under the flip of a coordinate, you very often do, that block diagonalizes the thing in two pieces. Now each piece is a matrix of some dimension d plus and d minus. And now usually you have to do real work. You have to compute in those blocks separately by diagonalizing your own computer. But the saving using the symmetry is enormous and totally essential. And never do a calculation without first using all symmetries. Now, I keep saying this because my students and do fluid dynamics for some reason never want to use symmetry because the pictures are pretty and they don't want to do calculation using this. If you're a chemist or condensed matter physicist, they teach you quantum mechanics in such a way that you don't know how to do any calculation without the symmetry. But this principle is true of all calculation, classical or quantum.